Okay, you're good. So this one says there's 0.3 mole of SO2 and 0.15 mole of oxygen is sealed in a 2 cubic decimeter container. Now, the moment you see something that isn't 1 cubic decimeter, like just make sure you remember it. Okay, because then it's gonna come in with the concentration. Okay, and then I give you the balanced equation and I also give you the enthalpy, the change in enthalpy. Okay, but for the first part of the question, we're not going to use that, so I'm going to come back to that later. Then they say at equilibrium, it is found that 0.1 mole of the SO2 remains. And then I ask you to calculate Kc. Okay, so I'm first going to do a Kc calculation, and then we're going to do some graphs because they sort of go together. Okay, so now they can ask you something like what's needed for it to reach a equilibrium, or what is necessary for a dynamic whatever. Okay, and then when we calculate Kc, I use the ICE table like that: initial, change, and equilibrium. And all three of those are mole values. And then in the last one, I calculate the concentration. So only leave the concentration stuff right until the end. Okay. So they give us that this one is 0.3 and this one is 0.15. And they are put in a container, so obviously there's nothing there yet. Okay, and we talked about how if these have a minus, then this one must have a plus, or the other way around. But the one side of the equation must become more and the other side must decrease. Okay. Then the only other information that they give us is that this is left at equilibrium. So this is down here at equilibrium. There's 0.1 mole. Okay, so now to calculate Kc value, we need these three. Nee, daai onderste drie. Because we know that the Kc value will be the concentration of SO3 to the power of 2 divided by the concentration of SO2, to the power of 2, and the concentration of oxygen, like that, because they're all three gases. So we need to take all three into account. Remember, only gases and anything that is in solution. Okay. So now the only column that we have enough information on is this one. Do you see that this decreased by 0.2? In the beginning you have 0.3 and at the end you have 0.1 left. So what happened is it decreased by 0.2. So do you agree that that means this one will increase 0.2? So for this one, you have to look there. The change, yes, the change row is the one where you look at the yes. Okay, so do you see that this one will be minus 0.1? Because it's 1 to 2 to 1, or 2 to 1 to 2. You're looking at that. Okay, and now you just work downwards. So this one we've already done. Do you see that here we'll have left 0.05? And here we now have 0.2. And now for each of them you use this equation. Like that. Okay. En nou het jy die waardes wat jy wil insit. So now we know that this one is 0.1 to the power of 2 over 0.05 to the power of 2 times 0.025. No unit, good. Okay. Do you know what a big Kc value like that means?
I think the concentration of the product is larger than the
Good.
concentration.
And this one is quite big, so it's larger by quite a bit than it is for the reactants.
I think if it's smaller than one, then it's other way around.
So when we are doing something like in the industry, when we're trying to make something in the industry and you want a lot of the product, then you're looking for a high Kc value. And that's where this bad boy comes in. Okay, so that's just the graph I drew of this reaction. But it doesn't matter, we don't need that top part for this. The only thing that we're going to use is did I say smaller than 0? Yeah. Okay. We're just going to look at that.
What do you mean by XLP smaller than 0? Or is that what it just gave you?
That they gave you that.
Okay. So how do I conclude to that?
No, that's written down.
Okay.
Yeah. So you don't have to study that or something. That'll be written down. So they gave you the balance equation. It's not balanced. And they give you that. All of that in one. Okay. So we're going to go through those 4 changes. And it's important that you realize this one is mole versus time. And the graphs for concentration versus time work the same. So this can either be mole or concentration. Okay, but do you see we started with 0.3 mole of this and 0.15 of this, and with nothing there. Okay, now, when we are looking at the shape before we start, it'll always either be this or this. So when a reaction is favored, then this will happen. In other words, it will increase and then reach a new equilibrium. Or when it is not favored, the opposite. So the opposite direction is favored, then this will happen. Okay. Only when we change concentration do we have a spike. So if it spikes up, then it means it goes like this. And if it drops down, that means it goes like this after that. And if you know that, then the shapes of these are quite easy to work with from there, because then you just need to figure out in which direction we're going. Hola! Don't have time. We don't have time.
Oh, I have to. So I just don't need to.
I'm recording.
So then how do you?
We'll make a plan. No? Yeah, we're gonna make a plan. Bye. Okay, you have that. Okay, so I'm gonna look at the 2 concentrations first. Now, for these, we need to know Le Chatelier's principles, meaning that if something is at the equilibrium and we change it then, so you have to see there it's reached equilibrium already. Do you see they flattened out? They're not changing anymore. So the concentration, yes, then they've reached the equilibrium. And they like asking questions like that as well. They'll ask you like, say that's T1. And they'll say, at what time increment did it reach its first equilibrium? Then you say at T1. Okay. So the fact that it flattens down tells you that it's reached equilibrium. Now we're going to disturb the equilibrium. So it is already at an equilibrium and we are going to disturb the equilibrium. So we're going to change either the concentration or the pressure or the temperature. Nothing else disturbs the equilibrium, only those 3 things. Okay. So if we disturb the equilibrium, then Le Chatelier wants to work against that. So if we decrease concentration, then Le Chatelier wants to increase it again. Okay, do you see that this is my product? Okay, how can we increase product? By favoring forward or reverse? Forward reaction. You're pushing it towards the product because we want to increase that. Okay, so now let's look at the shape of the graph. Let's start by saying if I decrease this one, it drops down. You see? Yes. And then it's forwarded. It's favored. The forward reaction is favored. Do you see? Okay, and if this one is favored, then everything on the other side of the equation has to be not favored, right? Because when it's in equilibrium, it's balanced, and now you're shifting the balance to the other side. So if we're shifting it towards the products, then it means these have to decrease because it has to take it from somewhere. So for that concentration to increase, you need to take away from those because they need to be forming the products then.
So when the concentration goes like that, is that it increasing?
This is a dip in the concentration. That's what we did. We took some of it out. This part. And this is Le Chatelier's reaction to that. Got it. Okay. Now let's look at this. If I dip the concentration of oxygen, what will Le Chatelier want to do? He will want to increase that. Do you see that oxygen is one of my reactants? So we're going to have to favor the reverse reaction. You agree? Meaning that if we go and draw this one, this will jump down, right? Because we decrease that, and then it's favored. So this one must also be favored, but this one will decrease. So do you see the jump is only in the one that we worked on. We only did something with the oxygen. We didn't do something with the other two.
When the oxygen's concentration is decreased, then what is the SO2? The SO2 increase at that moment, and then they flatten out.
Yeah, so all of them reach a new equilibrium there.
So at that point, O2 decreased, then SO2 increased to fill that up.
Do you see this one increased? This is Le Chatelier's reaction. But if we are favoring the reverse, then it means everything in the reverse has to be favored because we're shifting that way. So that's why this one is also increasing. And that's why this one has to decrease. Good. Okay. So those are the only ones that are going to have a dip and then a change. Now, when we're working with pressure, if we increase pressure, then Le Chatelier wants to decrease pressure. Okay. Pressure is decreased on the side with less moles gas. You have to know that. Okay, so which of the two sides has the least moles of gas? The reactants or the products? The products. So do you agree we are going to favor the forward reaction? Okay, so when the forward reaction is favored, it means that this one increases and these two will decrease. Because it's pushing towards the products. So if it pushes towards the products, then the reactants have to decrease. Do you see pressure doesn't have a stark increase or anything? Okay. Remember, it can look like this as well. If it's favored in the opposite direction. So if we decrease pressure, then the Chatelier will push it towards the side with the most moles of gas, which is our reactants. So then my reactants will increase and my product will decrease. Good.